Hello friends, welcome to engineering tutorial. Now in my previous two videos, I discussed about the common base configuration or connection mode of a bipolar junction transistor, and we discussed about the important parameters associated with common base configuration such as the current amplification factor alpha and the expression for collector current. And also we discussed about the voltage current characteristics, that is the input and output voltage current characteristics of a common base configuration BJT. So in today's video we will discuss about the common emitter configuration or the common emitter connection of BJT. The same, first we'll discuss the important parameters associated with common emitter connection, the current amplification factor and the expression for collector current, and then we'll discuss about the voltage current characteristics. So let's get started. So here you have this circuit diagram. It represents the common emitter configuration of a bipolar junction transistor. By seeing the transistor symbol, you can make out that it's an NPN BJT. It's an NPN BJT because this arrowhead, it is pointing outwards away from the base. It means that it's an NPN BJT. Now it also represents the direction of flow of emitter current, so the emitter current is flowing outwards. Now the collector and base currents, they are directed inwards in a NPN transistor. Now the PNP transistor can be also be connected. In that case, the arrowhead will be pointed inwards towards the base, and the direction of flow of all these currents will be opposite. So here in the common emitter configuration, this emitter terminal is common to both the input side towards the left and the output side towards the right. The input signal is applied between the base and emitter terminals, this signal, and the output is taken across this collector resistance, across the collector and emitter terminals. Now these VBB and VCC are the biasing voltages. VBB makes the base emitter junction forward biased and VCC makes the collector emitter junction reverse biased. You know, this base is P type, it's connected to the positive end of the supply, and this emitter is N type, is connected to the negative end of the supply, so it's forward biased. The output junction, this N type collector is connected to the positive end of the supply, VCC opposite, and this is connected to the negative end, so it's reverse bias. One of the ends connected to opposite ends of the supply means that's a reverse biased junction. So there's some important points again, you can note them down if you want. So basically the same things which I have said. So it's a common emitter configuration of NPN type BJT. The base emitter junction is the input terminal, the collector emitter junction is the output terminal. The emitter is common to both the input and output. VBB is the forward bias voltage, VCC is the reverse bias voltage. Now the weak signal, this one which is to be amplified, is applied across the base and emitter junction, okay, and the amplified output is taken across the collector resistance, okay. So next we'll discuss the important parameters associated with common emitter configuration in the same way we discussed in the common base configuration. So the two of the most important parameters in any BJT connection, be it any configuration, are the current amplification factor and the collector current. So here the current amplification factor is denoted as beta. In common base configuration it was denoted as alpha, here it is denoted as beta. Now we know that the basic definition of the current amplification factor, it is the ratio between the change in output current to the change in input current, okay. So here in case of common emitter configuration, you can see that the output current is the collector current and the input current is the base current. Okay, IC is the output current, IB is the input current. So the current amplification factor will be the ratio between a small change in collector current to a small change in base current. That is, small change in output current, small change in input current. So this is the current amplification factor, beta, for common emitter configuration. So here the beta value for common emitter configuration, that is the current amplification factor, normally always lies more than 20. It's always greater than 20 and falls in the range of 20 to 500. Okay, so the beta value, it falls in the range of 20 to 500, whereas in the common base configuration, the alpha value, it was always in the range of 0.9 to 0.999, because the collector and the emitter currents were nearly the same. The alpha was IC by IE, delta IC by delta IE, as collector and emitter currents were almost the same, so it was a value of alpha always approaches the unity 1. But in this case, the beta value is lies in the range of 20 to 500, because the magnitude of the base current is very less in terms of microampere, whereas collector current is in the range of milliampere. Okay, so that's why the beta value, the current amplification factor for common emitter configuration, is very high. Next is the relationship between beta and alpha. That is the current amplification factor for common base configuration alpha and the current amplification factor for common base configuration, common emitter configuration beta. Okay. Now, first we know beta is delta IC by delta IB, output by input current, and for common emitter, and alpha is delta IC by delta IE for common base configuration. We know these two things. Now, when we apply Kirchhoff's current law in a BJT, be it NPN or PNP, we always know that the emitter current is the sum of base and collector currents. So we can also write this as a small change in emitter current is equal to summation of the small change in base current to a small change in collector current. We can write it in this way. Now what we did here, we took this delta IC towards the left. Okay, so delta IB is now equal to delta IE minus delta IC. We just modified the expression in this way. Now, delta IB here is delta IE minus delta IC. So we put this value here, okay, in this delta IB for the expression of beta. So we got beta is equal to delta IC by delta IB. We wrote delta IE minus delta IC. Okay, beta is equal to delta IC by delta IE minus delta IC from here. Okay, so this formed another equation. We were marking it 1, 2 and 3. Okay, so you understood how this beta value came up. We put this value of delta IB here in the expression for beta. Okay, so beta is equal to delta IC by delta IE minus delta IC. Now, what we will do next is we will divide both the numerator and denominator with by delta IE. Okay, we will divide both the numerator and denominator with delta IE. So we will get the value of beta as delta IC by delta IE by delta IE by delta IE minus delta IC by delta I. So what we did here is, in the previous expression for beta, we divided both the numerator and denominator by delta IE. Now you pay attention, we know that delta IC by delta IE is the current amplification factor for common base configuration, that is alpha. So here we find or we get a relationship between beta and alpha. So beta is actually alpha by 1 minus alpha. Here delta I, they cancel each other out and we get 1. So actually the relationship between beta and alpha is this. Beta is equal to alpha by 1 minus alpha. So this is the relationship between beta and alpha. So next is the expression for collector current in common emitter configuration. Okay, so we'll derive the expression for collector current in common emitter configuration BJT. So in common emitter configuration, we know that the output current is the collector current and the input current is the base current, and also we know that applying Kirchhoff's current law in BJT, the emitter current is the sum of the base and collector current. Now if you remember, in common base configuration, the expression for collector current was in this form. IC is equal to alpha IE plus ICBO. Remember, the collector current consists of two parts. First part is the emitter current, which reaches the collector terminal, and this is the collector to base leakage current due to minority charge carriers. Okay, so the collector current consists of two parts for common base configuration. Okay, so we'll be using this expression for deriving the collector current expression in common emitter configuration. Okay, this expression of common base configuration will be used. So next, we put this expression IE is equal to IB plus IC here. So we get IC is equal to alpha into IB plus IC, which is IE plus ICBO. Now what we did is that we took the alpha IC part towards the left. So IC into 1 minus alpha, which is IC minus alpha IC, is equal to alpha IB plus ICBO. So dividing this expression with 1 minus alpha by taking it to the denominator, we get IC is equal to alpha by 1 minus alpha IB plus ICBO by 1 minus alpha. Now if you remember, we derived the relationship between beta and alpha just previously. Beta is equal to alpha by 1 minus alpha. So here IC is equal to beta IB plus ICBO by 1 minus alpha, which is the leakage current in common emitter configuration, which is called as collector to emitter current. Collector to emitter leakage current when the base is open. Okay, ICBO by 1 minus alpha. Okay, this IC is equal to beta IB plus ICEO, where beta is equal to alpha by 1 minus alpha, and this collector to emitter leakage current with the base terminal open is equal to ICBO by 1 minus alpha, where ICBO is the leakage current for common base configuration. Okay, do not get confused by these terms. ICEO is the leakage current for common emitter configuration. ICBO is the leakage current for common base configuration. This is the interrelationship between leakage currents of common emitter and common base configuration. Okay, ICEO is equal to ICBO by 1 minus alpha. Okay, now this ICEO is the leakage current for common emitter configuration. This ICBO is the leakage current for common base configuration. So this ICEO is actually the collector to emitter current with the base terminal open. Okay, so whenever you connect the BJT in common emitter configuration and you open circuit the base terminals, a current which flows due to minority charge carriers from collector to emitter terminal is the leakage current, which is a very small value and is often neglected. Okay, so it flows due to minority charge carriers, that is holes for NPN type BJT and electrons for a PNP type BJT. So this is the expression for collector current for a common emitter configuration. So we discussed the common emitter configuration or connection of BJT, and we discussed two important parameters associated with common emitter configuration, that is the current amplification factor beta, the relationship between beta and alpha, that is the current amplification factors for common emitter and common base configuration, and we also derived the expression for collector current in common emitter configuration. Now in my next video I will be discussing about the voltage current characteristics, that is the input and output characteristics of common emitter configuration. So I hope you like this video. Please subscribe my channel Engineering Tutorial for more such videos related to electrical and electronics engineering. Have a great day. Thank you very much.